Hello again, math friends, and welcome to the last part of section 3.4, or basically 3.4 continued. So in today's lesson, we're going to talk about solving exponential equations, but this time we're going to use logarithms. From before, we were solving exponential equations by matching the bases on both sides and solving the exponents, but now we're going to be using the natural sort of inverse of the exponential. We're going to use logarithms. So here are some great steps over here you see on the right. I'm going to kind of adjust them for us. But number one, great first step would be, why don't you isolate the exponential expression? And what I really think is, just try to get the base term isolated. Before you think about using any logarithms here, try to get the base term isolated. And if I just scroll down and look through a couple of these, if you look at number one, you notice that the base of this exponential is 3. And so the 3 to the x is isolated already. So good, step one would be done on that one. If I look at number two, the base is e, and you can see there the e to the x term is also isolated. But as I scroll down to maybe like number 5 and even look at number 6, the base here, the number that's being raised to a power is the 8. So that 8 to the 4 minus x is not isolated. There's some other things on that side that we're going to need to get rid of before we think about continuing. Okay, but that's a good first step, is try to get the base term isolated. And then once we do that, it says here in step 2, take the log of both sides, but I think of a better way is, why don't you go ahead and switch your in exponential form, why don't you switch to log form like we did before in class. Switch to log form. And then once we switch to log form, last thing you do is basically just solve for x. X should be free if you do it right when you switch to log form. So at that point, you can just get the x term by itself. So step 1, isolate the base term if it's not already isolated. Step 2, switch it into log form. And then step 3, we can solve for x. Easy peasy. All right, so for question number 1, here's what we're going to try. We have 3 to the x equals 80. And let's see, as we said before, the base is 3, and so the base term of 3 to the x is isolated, so good, step 1 is done. Next step, why don't we switch it into log form? As you remember, that's going to be log, the base here we said was 3, of 80 equals x. And if you want to check and see if that's correct, remember we use the arrows to go back and forth between exponential and log and back. So let me check. This would be 3 raised to the x equals 80. And is that what the original is? Yeah, it is. Good. So that means my log form is correct. Always good to check because it could change your answer if you put it in the wrong log form. All right, that's great. That means x is already isolated. All we need to know is figure out, how do I put that in the calculator? Because you remember the calculator log is log base 10. This is log base 3, so how do I do that? So off to the side, what I'm going to do is I'm going to put little steps over here. To do a log that's not a base of 10, first you're going to go in your TI-84, whatever you have, go to the math button on the left-hand side. And you see all the choices for choice 1, choice 2, and so on and so forth. Then you go down. On my calculator, it's actually choice A, but the choice says log big base. You want to use that button if you want to use a logarithm that has a different base than 10 that's on your calculator. So go down and select the A or log base. When you open that up and hit enter, on your screen you're going to see this, log, a little empty square where you can put the base, and a big empty square where you can put the argument that's inside your log. So if I go back to what I had up here, mine was log base 3. So in my calculator over here, I'm going to put a little 3 here and move my arrow into the big square. And as you see, the argument inside the log is 80, so I'll type in 80. And then I can enter. And when I do that, my answer is x equals, I get about 3.9987. 9887. And generally we'll try to round things maybe to 2 decimal places. This is about 3.99. And that's the answer for number 1. So again, to review the steps, what did we do first? We tried to get the base term all by itself. And once it was, we put it into log form by using the new log base formula on our calculator. And then we solve for x. Let's try number 2. All right, number 2. First step, let's see, is the base term isolated? The base is e, and so e to the x is isolated. So step 1 is done. Let's switch into log form. But ooh, this is a special one, right? This is log with an e base, and we don't write it like that, remember? This is the ln. This is natural log. So when I switch an e base into log form, make sure you use the ln. All right, this is going to be ln of, well, base e, but I don't have to write that. ln of 140 equals x. Good thing is we have an ln button on the calculator, so we can type in ln of 140 right away, hit enter, and I get 4.9416. I'm going to round to about 4.94. And that's number 2. You can always check these answers if they're right, folks, because you're solving using algebra, and you can always plug the x back into the original to see if it's right. What if we did that? So you take the original and say e to the x, and your x was 4.94. E raised to that, and hit enter, and you should get really close to 140. It won't be exact, because remember we rounded our x answers, but it should get really, really close to that number on the right-hand side. All right, let's get a little bit tougher. How about number 3? If you're feeling comfortable and you want to pause the video and try it on your own, then come back, go for it. All right, the base here is 5, and the 5 to the x plus 1 is all by itself. I know there's an x plus 1 exponent. That looks a little weird, but the term in yellow here is by itself, so we're ready for log form. Here we go. Log base 5 of 18 equals, and the x is free. All right, now, what I can do is I can put this in the calculator right now, but I'm going to do something a little different. I'm going to keep it like that because I'm a little worried that I might round my answer too early. That means my final answer might be really rounded. So why don't we solve for x, and then we'll put everything in the calculator. All right, over here, there's some extra stuff to do. We have to subtract 1. All right, that means this is log base 5 of 18 minus 1. Now, really important notice here. I'll put a little star here. The 18 here, folks, is inside the logarithm. The minus 1 is outside the logarithm. We cannot combine these together. That's not legal in math. The 18 is inside the logarithm, and the minus 1 is outside. So we can't do anything with that. Just it is what it is. So that is x. All right, ready? Let's put in that calculator. Let's put log. We'll use our new log button over here on the left side that we learned. Log base 5 at 18. When you do that, it should open up a parenthesis for the 18. So close it before you put the minus 1. So the minus 1 is on the outside. Hit enter, and you should get x is about, I get about 0.7959. Why don't we just round that to 0. Oh gosh, maybe 80. And there you go. So sometimes there's a couple of extra steps you have to do after you switch into log form, and then just maybe save the calculator for the last step. Good job, everybody. Let's keep going. How about number 5? Again, if you want to pause the video and try it on your own, go for it. Okay, now this is the first case on number 5 where the base term, e to the 3x, is not isolated. Do you notice the 25 on the same side? We need to get rid of that. Way to get rid of that, let's just do some algebra and subtract 25 from both sides. All right, that gives us e to the 3x equals 108 minus 25 should be 83. All right, so now I think the base is all by itself. Let's switch to log form. This is e, so our logarithm is going to be ln, natural log. This should be ln of 83 equals 3x, and the x is free. All right, before I put in the calculator, why don't we just go ahead and keep going? Let's get the x by itself by dividing both sides by 3. But like we said before, this 83 is inside, this 3 on the bottom is outside. So we can't reduce that. Don't be tempted. Just leave it alone. And let's just type it in. So x equals ln of 83. And just like before, if there's anything outside the log, go ahead and close this parentheses before you hit divided by 3 on the bottom. All right, if I do it right, my x is about 1.4729. I'm going to round it to 1.47. How are we doing, folks? Doing okay? Great. Here comes number 6. Another instance where the base term, the e to the, is not by itself. What's happening? Looks like it's being multiplied. So why don't we divide? I'll divide both sides by -2 to get that out of the way. And I should get 8 to the 4 minus x equals negative 50 divided by negative 2 is positive 25. Our base term is isolated, so why don't we go ahead and switch this into log form. This is log base 8 of 25 equals 4 minus x. And again, before I use calculator, let's just go ahead and keep the x by itself. And so I'm going to subtract 4, and that should be log base 8 of 25 on the outside minus 4. The negative x is still there, so last step, I'll just divide both sides by negative 1. Okay, if you put that in the calculator in one step, it should work. Just make sure you put the 25 in parentheses. Now, if you want to try the whole thing in one big step, that's great. But here's what I would suggest. If you do that, start the whole numerator expression with one parentheses. Type the log base 8, open the green parentheses and close them around the 25. And then after the minus 4, close your numerator before you hit divided by the minus 1. So the entire numerator is in its own parentheses. And let's see if we did it right. I got about 2.4520, or about 2.45. How did you do? All right, why don't we try one more? Number 8 looks great. All right, for number 8, can you find the base term? For me, the base term is the 4 to the, and there's a lot of stuff happening around it. Can you spot it? Yep, I see the negative 2 is multiplying it, the plus 9 on the outside, but which one do you have to get rid of first? Well, remember, when you're isolating terms, you usually want to get rid of the addition and subtraction first. So I'm going to subtract 9 because that's the most outer action happening. And then I'll divide by negative 2. But right now, I should have negative 2 times 4 to the 2x plus 7 equals negative 55 minus 9. How about negative 64? Almost isolated. Let's divide both sides by negative 2. I get 4 to the 2x plus 7 equals positive 32. My base term is isolated successfully. Let's switch into log form. I've got log base 432 equals 2x plus 7. So now our x is free. That's awesome, but there's a lot of stuff happening. Can you get that x by itself? Here it is. And remember, the most outside thing to get rid of on the right side should be the 7 first, and then we'll get rid of the 2. So if you can see it, I'm going to put in one big step here. Did you get this? I would get x equals log base 4 of 32 minus 7 whole thing divided by 2 by isolating the x. Did you get the same thing? Awesome. If you want to put it in one big step, let's start the whole expression on top with a parentheses. When you get to 32, close that parentheses, and then surround the whole top by a final parentheses before you hit divided by 2. And if you do it right, you should have gotten about negative 2.25. Did you get that? I did too. Great job on that. Awesome. Okay, let's take a pause for a sec. All right, welcome back. We started this whole section with the idea of what if we want to find out how long it takes a starting amount to reach a final amount. How long would it take if we put $100 in the bank and we want to reach $1,000, and we know how much is being compounded and we know how much the interest rate is going to be? What is the time? And we learned that in order to do that, we're creating an exponential equation that we're going to have to solve. But it's going to be like we just did before. We're going to have to use logs. All right, first of all, we need to bring back that old equation for compound interest. Do you remember? P of t equals P of 0, 1 plus the interest rate divided by the n. And n was what you were compounding, how often. Outside raised to the n times t. So if we try this one, this is going to be, well, I know what the final is. It's $1,000. I want to get $1,000 by starting with 100. And I've got 1 plus, interest rate is 7%. Remember how we would switch that to a decimal by saying 0.07. Okay, 0.07. And this is monthly, which means compounding 12 times per year. So I'll put the 12 here. I'm going to raise to the 12 times t. Let me put the t in blue here. All right, look at that whole equation. We have numbers everywhere, but the only variable that we have to solve for is the t. But notice it's in the exponent, so this is truly an exponential equation, so we're going to have to use logs. But the trick here is we have to isolate the base first, like before. Well, first of all, what the heck is the base? Well, if you see, what's the term that's being raised to a power? It's the parentheses. This parentheses term, the 1 plus 0.07 divided by 12, is what's being raised to the 12t. So the green underline is your base. We need to get that by itself. And the only thing that's interrupting that is the starting amount. So the starting amount is multiplying it, so we have to divide. So first step on these problems, we're going to divide by the starting amount. All right, when I divide 1,000 by 100, I basically just get 10. So 10 equals 1 plus 0.07 over 12 raised to the 12 times t. All right, this crazy base, as weird as it looks, is now isolated, so now we can switch into log form. But this is a very hard one to do because the base is so complicated looking. So a good trick is, if you don't want to write this whole base as you see here, you can just replace it with a big X. And what we can do here is, well, why don't we actually put this X into the calculator and see what it looks like? What is 1 plus 0.07 divided by 12? Well, let me put that in. How about 1 plus 0.07 divided by 12? And I get about 1.00583333 and so forth. Okay, the good thing is I have that in my calculator right now. So later I can use my answer button or ants to put that in. Okay, but visually when you write this, here's what I'm going to do. I'm going to say 10 equals, I'm just going to call it x, and that's the base, the parentheses, the 1.0058333 that I don't want to write again, and we're going to raise it to the 12 times t. All right, that looks a little bit simpler, so I'm going to keep it as a big X, even though I know X is really this number over here, and I'll use my answer button in just a sec. I just think this looks a little bit pleasing to the eye, and a little bit easier to switch into log form, which is what we're going to do next. Ready? Here comes log form. This is log base. Well, the base is the X, and it's so much easier to write it if it's just an X and not the 1.00583333, or even as the big green underline up here. Ooh. So an X is just simpler to use if you like that method. This is log base X of 10 equals 12t. And now the t, the variable, the time, is free. Yay. So now I'm going to divide both sides by 12 to get the t by itself. And now t is log base X of 10 divided by 12. Now when I put in the calculator, I'm going to use that log base button again, and it's going to open up log, and the base, I'm going to put my answer button. That's a great time to use the answer button because then it'll copy it, the whole exact number that you had here. You didn't have to round it. You don't have to retype it. So log base answer of 10, and when you close that parentheses around the 10, then you can hit divided by 12. Let's give it a shot and see how we do. So I'm going to do math button, go to my log base button, and under the little base, I'm going to put second negative sign, which is the answer of 10. And I divide by 12. And it looks like it's going to take me about t equals to go from 100 to $1,000. It's going to take about 32.9899, or we can just say it's going to take about 33. And this time is always in years. So that's pretty good. If we want to try to go from $100 to $1,000 just by letting it sit in the bank, compounding monthly, 7%, which is a good interest rate, it's going to take about 33 years. Let's look and see how we did that. First of all, always remember the compound interest formula. Once you set it up, the base is going to be that crazy parenthesis there. And so the first step we usually do is we divide by the deposit or starting amount. And then we're ready to go into log form. But to make it a little visually easier, I'm going to switch this into an X. And then when I get into log form, it looks more like this. But along the way, before I put that in the log form, I put the X into my calculator just so I had that number, and I replace it with an answer when I put it into the base of my log button. Solve for t, get it by itself, and it's good to go. There you go. Should we make up a really fun one? Another fun one you can try is, what if we want to go from $1 all the way to $1,000,000? Let's say we're going to compound continuously, and we're going to have an interest rate of, let's say, 6.25%. So how long is it going to take from $1 to $1,000,000? It's going to take a really long time just sitting in the bank. But hopefully you noticed I used the word continuously. When we talk about continuously, that's a different formula, right? P of t equals P sub 0 times e to the RT. This is the PERT formula. This is continuously, so we always use the E one here. All right, ready? Let's plug in. So I know I want to end up with $1,000,000, and my starting amount is $1. E to the R is 6.25, which we changed to 0.0625. Okay, I'll put that in there. 0.0625 times t. T is in blue. Okay, well, the base here is E. And there is something in the way, but it is just a 1. So right now we don't have to worry about it. But just to get good practice, I'm going to divide both sides by 1 because we should always divide by our starting amount first. Okay, that's not going to change anything. So dividing by 1 just gives us, again, 1,000,000 equals e to the 0.0625 t. And the base of e is now all by itself. So shall we switch to log form? Here we go. But remember, this is e, so the log will be ln. ln, base of e, of $1,000,000 equals 0.0625 t. This one's a little bit easier than the previous one because the base here was e, not that crazy parenthesis that we had in the previous one. So this one's a little bit easier to set forth. All right, to solve for the t, one more step. I'll just divide by that rate on both sides before I use my calculator. All right, ready? Drum roll. As we put this in, what is the ln button? ln of 1,000,000. Close my parenthesis, and I'm going to divide by 0.0625. I thought it's going to be a big number. Oh, it really is. Well, it won't happen in our lifetime, but my calculator says it's going to take about 221 years. My goodness. Well, put it in, save it for your great, great, great grandkids, and they'll be happy and rich. And that's how we use logarithms to solve exponential equations, especially ones with money. Great job, everybody. See you next time.